Okay, thank you for the invitation to come speak here and for putting together this nice conference. This topic, topologically ordered matter and why you should care, is a very popular subject in condensed matter physics, and most of the people attending this Topmat conference are condensed matter physicists. However, it's also a subject that cuts across a number of other fields of modern physics. If you're from the quantum information community, you probably heard a lot about topologically ordered matter, possibly in disguise as error-correcting codes. And if you're in the high-energy physics community, some of these ideas might also sound familiar to you, because actually some of the ideas that we work on, things like topological quantum field theories, they came out of the high-energy community starting in the 1980s, more or less, with people like Ed Witten thinking about topological quantum field theories. However, so no matter what field you come from, I hope you will get something out of this talk and you'll learn something new. However, the real origins of this field go back much further into the 1800s, and that's where I'd like to start my story. So in 1867, there were two very well-known physicists living up in Scotland. The first one by the name of William Thomson, better known as Lord Kelvin. I probably don't have to tell you all the wonderful things that Lord Kelvin did and discovered. The second one was his very close friend, a guy by the name of Peter Tate. Now, with the exception of people who have heard my talk before, how many people know the name Peter Tate? Very few. Okay, well, he deserves to be well known. He was a great scientist in his own right, and he communicated with Lord Kelvin throughout his life. In 1867, they were actually interested in a phenomenon of fluid flow that was familiar to them and also familiar to pretty much everyone in the world. It's the phenomenon of a vortex loop or a smoke ring. So let me remind you what that is. You imagine an invisible loop in the middle of the air, and the fluid, the smoke in that case, rotates around this invisible ring in the air, and the entire ring comes out of the plane of the board out at you. See, back in the old days, in the 1800s, they used to do this weird thing called smoking tobacco, and they don't do that anymore. But back in the old days, right? So back in the old days, they used to do this, and a talented smoker could produce a smoke ring out of their mouth, and so everyone in the world had seen smoke rings, and Kelvin and Tate wanted to study this. So Tate built a machine to blow smoke rings. It's actually quite easy to make such a machine if you've never done so. It's kind of fun to play with. You take a tube, like maybe a garbage can or something, you fill it with smoke, you hit the back of the tube, and a smoke ring comes out the front. Rather impressive things to play with if you've never done so. You can see videos of it on YouTube now. I recommend you looking them up. But anyway, Tate showed this to his friend Lord Kelvin, and Lord Kelvin was very impressed, and he had a number of simultaneous epiphanies. The first epiphany is something that we still teach in undergraduate fluid dynamics. It became known as Kelvin's circulation theorem, and the content of the theorem is basically that the only reason this smoke ring ever dissipates, the only reason it stops rotating, is because air is not, or smoke, is not a perfect fluid. It has friction, viscosity, dissipation. If it were not for that, the smoke ring would just keep spinning around and around and around and around in the air, and it would just last forever. Now, that got him thinking, where can you find a perfect fluid that doesn't have any dissipation, any friction, or any viscosity? Now, such perfect fluids do exist. We call them superfluids. For example, if you take helium and you cool it down to below 2.7 Kelvin, it becomes a superfluid, and a vortex ring like this in superfluid helium really will last essentially forever. But Kelvin didn't know about that. They certainly didn't have any cryogenic apparatus to cool things down to very low temperatures, and in fact, in 1867, it was a few years before helium had even been discovered. So he didn't know about superfluid helium. However, he thought he knew about a perfect dissipationless fluid. It is a famous mistake in the scientific literature. It's a mistake in the literature known as ether. So let me remind you what ether was. Ether was supposedly this perfect dissipationless fluid that filled all of space, and its purpose was to convey electromagnetic waves. And they knew an awful lot about waves. They knew that when they saw a wave on the water, what they were actually seeing was water sloshing back and forth. They knew when they heard a wave of sound in the air, what they were actually hearing was the air moving back and forth. And they knew that light had wave-like properties. Light is a wave. But they didn't see anything moving back and forth, but they hypothesized that such a material should exist, and they called it ether. And this idea of ether actually goes back several hundred years earlier to René Descartes, who thought it up. He said, I think, therefore it is, and he thought that was a joke, in case you missed it. So I think he's thought this stuff up, and it was very convincing to the scientific community, and it was basically accepted as truth in the 1800s that the universe was filled with this ether stuff that carried electromagnetic radiation. And this ether had to be extremely dissipationless because you can see light from stars extremely far away, and if there was any dissipation or friction at all in this ether fluid, we wouldn't be able to see the stars. So Kelvin had, on the one hand, this circulation theorem that tells him that a smoke ring would last forever. This fluid flow configuration would last forever if it weren't for the dissipation in the fluid. And on the other hand, he believed in this ether stuff, which is a perfect dissipationless fluid. So that got him thinking, what is a smoke ring like this in the ether? And he came to a rather remarkable conclusion. He said a smoke ring in the ether is an atom. So for example, this might be a hydrogen atom. And you can have something more complicated where you have, say, two rings that are linked with each other, like this, and the fluid would flow around this one like this, and the fluid would flow around this one like this, and maybe this is a hydrogen molecule. And because of his circulation theorem, this would be stable for all time, because there's no dissipation in the fluid. And you could have something even more complicated, like, see if I can draw this, maybe like this. A knotted loop here, and the fluid's actually flowing around the loop this way, and like this way, and like this way, and like this way, and so forth and so on. And this fluid flow configuration is completely stable for all time, and maybe this is a more complicated atom, like maybe it's lithium. Now this sounds completely bonkers to us right now, because we know that atoms have nothing to do. We know that ether doesn't even exist. We know atoms have nothing to do with smoke rings in the ether. We know atoms are made of protons and neutrons and electrons and things like that. But it sounded like a really good idea in 1867, and a lot of very serious scientists thought that this might actually be true. People like Maxwell and Kirchhoff and Helmholtz and all these people really liked this theory, what became known as the Vortex Theory of the atom. Although some people criticized it, and quite early on, one of the people who criticized this theory was Peter Tate. And the reason he criticized the theory was because he said, well, it's a nice, beautiful picture, but it doesn't predict anything about the atoms that you would want it to predict. You would want it to predict the chemistry of the atoms, the masses of the atoms, the optical properties, the electrical properties, all these things you would want a theory to predict. It doesn't predict, so it's probably wrong. Anyway, for about 10 years, the scientific community took this fairly seriously, during which time Peter Tate was not paying attention to this development. Instead, he was out golfing. As it turns out, Peter Tate was a fabulous golfer. Is anyone here a complete golf fanatic? No? I still haven't found someone who's enough of a golf fanatic. Peter Tate's son, Freddie Tate, was a famous golfer. He was a champion of the British Open. There's a Freddie Tate Cup named after him that's still awarded every year. Anyway, so he and his son went out golfing every day during the late 1860s and 1870s, completely ignoring this development in science. At the end of 10 years of going golfing, he actually wrote some beautiful papers on the flight of golf balls, and he was instrumental to putting the dimples on golf balls, explaining that would make them fly better and so forth. Anyway, so he was really into golf, but he wasn't paying any attention to this. At the end of 10 years or so, most of the scientific community had given up on the vortex theory of the atom for exactly the same reasons that Peter Tate had espoused early on, that it just didn't seem to predict anything useful about the atoms. But at the end of those 10 years, Peter Tate went back and re-examined this theory, and he said, well, it may not predict anything about the atoms, but it's such a beautiful picture, maybe it's right. And so he decided that what he needed to do is he needed to devote the remainder of his life, or much of the remainder of his life, studying this theory of the atom, this vortex theory of the atom. And he felt that the right way forward was to make a periodic table of all possible knots. And he thought if he could make a periodic table of the knots, this is the simplest knot, this is the next most simple knot, this is the next most simple knot, and so forth and so on, he would learn something important about the periodic table of the elements. So he embarked on his life achievement, which was to develop what we now call the mathematical theory of knots, or knot theory, and he is rightly viewed as the father of this field of mathematics, which is an extremely important and rich and beautiful field of mathematics. And actually has a lot of relevance to what we're doing here in physics, which I'll explain as we go along. So I will get to the point of what it was that Peter Tate discovered that's important for us in topologically ordered matter. But before doing so, I have to tell you the end of the Peter Tate story. So around 1900, Peter Tate had learned an enormous amount about the theory of knots. In fact, some of his conjectures about knots were not proven until over 100 years later. So he had amassed an enormous amount of knowledge about knots, but of course he's no closer to understanding the periodic table of the elements. Had he lived till 1905, of course Einstein comes along and teaches us that there's no such thing as the ether anyway, and this whole idea is garbage. But he doesn't live that long. In 1900, he's already starting to get rather old and somewhat depressed, because he spent his entire life working, or much of his life, working on this vortex theory of the atom, and he feels it's not going anywhere. There are some letters from him to Kelvin expressing his dismay about having put so much effort into this, and it wasn't getting any closer to understanding the periodic table of the elements. And then in 1901, his son Freddie, the champion golfer, was killed in the Boer Wars extremely young. That put Peter Tate in a very, very deep depression, and he dies only 2 months later, extremely sad, a rather terrible end for a great scientist. OK, so with that sad story, let me go on and explain what it is that Peter Tate figured out, which is so important for us. So what he put his finger on is the fundamental question in the theory of knots, is how do you know when two knots are equivalent and when they're not equivalent? So I'm going to draw another knot on the chalkboard here, a very simple one, like this. And the question is this knot the same as this knot, or is it different? And when I say the same, sometimes we say topologically equivalent, which means that can I take this picture here and turn it into this picture without cutting, without using scissors? Now, we're all pretty smart people here, and we can tell that if you just unfold this picture, it would be an open loop like this. So these two are topologically equivalent. This question, it seems rather simple in this case, turns out to be extremely difficult when you get to more complicated knots. For example, it was about 20 years later down the line, after Peter Tate's death, that someone managed to prove that this knot is actually inequivalent to its mirror image. So actually showing the two knots are the same or different is actually quite a difficult task. And what Peter Tate realized is you need some sort of mathematical tool to help you out. So now I'm going to take a little bit of a detour into the theory of knots, and I promise I will get back to physics in a moment. So the tool that Peter Tate understood is what we now call a knot invariant. We never used this word. The word came along later. And a knot invariant is a mapping from an input, which is a knot, to some output. And the output can be a number, or it can be a polynomial, or it could be some mathematical symbol. But the mapping from the input to the output is via some set of rules. And the key part here is that the rules are cooked up in such a way that topologically equivalent knots, in other words, knots that can be deformed into each other without cutting, have to give the same output. So if you have two knots and they're complicated and you don't know if they're equivalent or they're inequivalent, you put them into the set of the rules, you get two outputs. If the outputs are different, you know immediately that these two things cannot be deformed into each other in any way without cutting. Okay? Very, very powerful tool to have at your disposal if you're trying to build a periodic table of knots. So to show you how this works, I'm going to define a particularly useful knot invariant known as the Kaufman invariant. It is not an invariant that was known to Peter Tate. It came along in the 1980s. The Kaufman invariant, of course, was named after his inventor, von Jones. So von Jones is a famous mathematician who won a Fields Medal, that's the highest prize in mathematics, for his work on the theory of knots. But the reason it's actually not named after it, that was a joke there also, that it's named after Kaufman, not after Jones. The reason it's named after Kaufman, not after Jones, is because Kaufman, a very important mathematician as well, not a Fields medalist, did something that I think is at least as important as what Jones was doing, and that is he managed to simplify what Jones was doing. Jones is famously obtuse, he simplifies what Jones is doing to a language that's so simple that I can explain it to you in about 2 minutes, and that's what I'm going to do. Okay? So to define the Kaufman invariant, the first step is you have to choose a number. We'll call it A. A stands for a number. That's why we call it A. And for now, we're going to keep this number just a variable, but later on we might give it a value. And then the first rule we have is that if you ever have a loop of string in your knot with nothing going through the loop, you can replace that loop of string by the following combination: minus a squared minus a to the minus 2, okay, in terms of that variable a. And this combination, minus a squared minus a to the minus 2, shows up so frequently, we give it its own name. We call it d. So the first rule here is simply that a loop of string is worth d. The second rule is a little more complicated. If you have a picture with two strings that cross over each other in a picture of a knot, you can replace that picture with the sum of two pictures. So in the first picture, you get two strings going in the vertical direction, and you get a prefactor of a. And in the second picture, you get two strings going in the horizontal direction, and you get a prefactor a inverse. Okay? So what am I doing here? What I'm doing here is I'm doing algebra with pictures of knots. So I took a picture of a knot, I replaced it with the sum of two pictures of knots, and I've given them prefactors. Okay? If this isn't clear, I'm going to do an example to make it clear in a moment. Now, these are the only two rules we need, but I'm going to cheat a little bit and draw a third rule. And the third rule is exactly the same as the second rule, except all the pictures are rotated by 90 degrees. Okay? Plus a inverse times vertical. Okay? So it's exactly the same rule, but all the pictures are turned. And the reason, so it's really the same rule, just looked at it from the side. The reason I'm drawing the rule twice is because it's easier for me to draw the rule twice than it is for me to ask you to rotate your head in a few minutes. Okay, so that's why I'm doing this. Okay, so to demonstrate how easy this is, I'm going to evaluate before your very eyes the Kaufman invariant of this particular knot. I promise I'm going to get back to physics at some point before the end of the talk. So what do we do with this picture of the knot? We'd like to evaluate its Kaufman invariant. And the way we do it is we focus in on one of the crossings in this knot. So here's a crossing right here, that little red loop. And we look at it, and the sense of the crossing is exactly like we have over here on the top picture. Okay? So what we can do is we can replace that crossing with a times vertical plus a inverse times horizontal. Okay? So far so good? Happy with that? And then we just fill in the rest of the picture exactly as it is over on the left. This, exactly as it is over the left, and over the left it looks like this, looks like this. Okay? Does everyone understand what I'm doing? No questions? Everyone happy? If you understand this, you'll understand everything else for the rest of the day. This is the most important moment of the day. Okay? Besides waking up or something, I don't know. All right. So now in these pictures, what we have is we have two crossings left. This crossing here and this crossing here. So I'm going to try to apply one of these Kaufman rules to get rid of that crossing too. And you'll notice that this crossing is in the sense of the lower picture over there. So we have to apply the rule at the lower picture. So we're going to do this fairly quickly. Take this whole thing down to here. It equals, OK, so I'll open up a bracket. So this a comes from here. Open up a big bracket. And then we have a times horizontal plus a inverse times vertical within that red loop, and then fill in everything exactly as it is upstairs, like this. OK? And then do the same thing for this knot here. So a inverse, that's this a inverse here. And then this crossing is a times horizontal plus a inverse times vertical, and fill in everything like it is up here. So I guess it's like this, and this like this, if I didn't make any mistakes. OK? Everyone happy? OK, good. So now I've reduced all the pictures to just loops. There's no crossings left. So then I can just apply the first rule, giving each loop a factor of d. So let's put all this together. equals, OK, so here we have two a's and two loops. So I have a squared times d squared. And here I have a cancels a inverse one loop, so that's worth d. And here I have a cancels a inverse, and I have three loops, so that's d cubed. And here I have a inverse times a inverse in two loops, so that's a to the minus 2 d squared. OK? So we're almost there. Here I'm going to use one little bit of algebra. I'm going to notice that I can put together a squared with a to the minus 2. And if you'll notice that a squared plus a to the minus 2 is the same as minus d. So I can replace those two, put them together, and get a minus d cubed from these two. The minus d cubed cancels this d cubed. And the whole thing at the end of the day is just this d left over and nothing else. Yay. So that's very exciting. So why is that so exciting? That's the end of the calculation. So the reason this is so exciting is because at the beginning, I started out with this sort of kind of complicated looking figure 8-like kind of knot. But secretly, we knew that this was just a simple loop. Now, a simple loop by the Kaufman rules gets the value d. We tried to make it look more complicated by folding it over. But at the end of the day, it still gave us d. And I could have folded it over 100 times or 1,000 times, tried to make it look really, really complicated. It still would have given me d. Okay? That's why this, the idea of this knot invariant is really powerful. It doesn't matter how complicated you try to make it look. It's always going to give you the same result. OK. So you can imagine why it is that this is a useful thing to have if you're trying to build your periodic table of the knots. Now, if you think about it a little bit harder, though, you'll realize that maybe it isn't so useful after all. Why? Well, the computation of the Kaufman invariant is something that's exponentially difficult in the number of crossings you have. What do I mean by that? Well, in this picture, I started with 2 crossings, and I ended up with 4 diagrams at the end of the day. 1, 2, 3, 4 here. Now, if I had 3 crossings, I would have had 8 diagrams. 4 crossings would give me 16 diagrams, and so forth and so on. Now, it's really, really easy to draw a picture of a knot with 100 crossings in it. 2 to the 100th power is such a big number that the world's largest computer working for the age of the universe would not be able to write down all of the diagrams that you'd end up with at the end of the day. So that makes it seem like this is actually not such a useful thing after all. So we'll come back to that in a little while. OK, so with that as an introduction, I'm now going to switch topics and talk about something that sounds like it's different, but actually turns out to be almost exactly the same. And that is the idea of a topological quantum field theory. So let me write it down, because we kind of need to know what it is. OK, so is there a question? Someone? Yeah? Yes? Yeah, OK, so the question is, if 2 knots have the same Kaufman invariant, is it possible they're different? Yes, it is possible they're different. The simplest 2 knots that are known with different Kaufman invariant, with the same Kaufman invariant, which are different knots, have something like 16 or 18 crossings or something like that. So they're fairly complicated knots, but there are examples known of 2 knots which cannot be distinguished by the Kaufman invariant. An important open question in knot theory is that if any knot which is not the simple loop has a Kaufman invariant which is just d. That's not known. And another important question is whether you can find a similar invariant of this type which can distinguish all knots from each other. And there are conjectures about that, but there's no proof of it. OK, so we'll now move on to the idea of a topological quantum field theory. And that sounds kind of fancy, but it's actually a fairly simple thing. The idea of a topological quantum field theory is that it's any quantum system or field theory that you can write down that where amplitudes, quantum mechanical amplitudes, depend on topology rather than detailed geometry. Let me repeat that because it's important. Amplitudes depend on topology rather than detailed geometry. Now I'm going to give an example of this in a second here to try to make it a little bit clearer what I mean by that. So first of all, I should warn you that I'm sort of a two-dimensional guy, and everything I'm going to be saying today, it applies to two-dimensional systems, and I'm going to draw the third dimension sort of upward. So 2 dimensions flat, and then a third dimension time is going to go upwards. So here's a picture of a two-dimensional system. It's a flat system like this, and time goes upwards like this. Time is upwards here. Time is money. Money is upwards. I don't know, something like that. So time goes upwards like this. And we can imagine writing down all sorts of processes that can occur in time, starting with the system in some particular state. So let's imagine that this system, this two-dimensional system, starts in its ground state, or we can call it the vacuum state if you like. So there are no particles sitting around. There's nothing there. It's just the vacuum. But then at some point in time, we can imagine adding some energy, maybe a photon or something like that, to the system. And that energy can create a particle-antiparticle pair, or in condensed matter, we call it a particle-hole pair sometimes. And they come out of the vacuum, and they pull apart from each other, having put in the energy. Now you can do the same thing, put in some energy later, and create another particle-antiparticle pair, like this. And then maybe one particle, we drag it around another particle like this. And then maybe we bring them back together like this, and we try to re-annihilate them back to the vacuum. Now, when you bring them back together, various things can happen. Question mark. What can happen? One thing that can happen is they can re-emit their energy in the same form that you put it in, as a photon. The photon leaves the system, and you're back to exactly the same state that you started with. But another thing that can happen is they can form a bound state which refuses to emit its energy back to the vacuum, and you're just stuck with this bound state. Now, we're not so surprised that in quantum mechanics you can have multiple results of a single experiment, because results in quantum mechanics can be probabilistic. So you do the experiment many times, you get some results one time, you get another result another time, and you measure the probabilities of either happening. So let me draw another picture over here. This is supposed to be exactly the same picture, despite my inability to draw it so. So we start with the system in its vacuum state. And then let's put in some energy here, create the particle-hole pair. Maybe put some energy in over here, create the particle-antiparticle pair. Maybe drag this particle around this one, like this, and then annihilate this one over here, and maybe annihilate this one way over here. Okay? And again, you have the same question mark at the end. There's some probability that it re-emits its energy back to the vacuum, and some probability that it forms a bound state. Now, in a topological quantum field theory, the probabilities of it going back to the ground state in these two pictures are exactly the same. Why? Because the definition of a topological quantum field theory is that amplitudes, and probabilities of being the square of amplitudes, depend only on the topology of the picture and not on the detailed geometry of the picture. The fact that this can be deformed into this continuously, topologically deformed, that they're topologically equivalent, tells you that the amplitude, or the probabilities that you measure at the end of the day, are equivalent in those two pictures. And that's what makes this a topological quantum field theory. Now, the idea of thinking of topological quantum field theories this way was very famously made by Ed Witten, who went on and showed that these amplitudes, these probabilities, they themselves are not invariants. By definition, these things are not invariants. They're an output that depends only on the topology of the input via some set of quantum mechanical rules. Okay? And thus, the output of our topological quantum field theory experiment gives us some particular not invariant of our physical system. All right, so this was rather a remarkable advance. Ed Witten, probably people know the name, one of the world's foremost string theorists. He won his Fields Medal along with Vaughan Jones for work on knot theory. And one of the things that he did, which was so beautiful in this, well, he did many, many things which are very beautiful in this one first paper, which connected together knots and topological quantum field theories and conformal field theories and lots of other things. But one of the things he did that was so interesting is he took a bunch of known topological quantum field theories, which I'll give them a name. Name isn't important exactly what they are, what the name is. They were called SU2 level K topological quantum field theories, or Chern-Simons theories. SU2, people probably recognize that. That's the rotations of of quantum mechanical objects in 3 dimensions. And K is a coupling constant, which has to be an integer. And he related the knot invariance you get from experiments in these topological quantum field theories to the Kaufman invariance. With the mapping, all you have to do is you have to pick the right value of this A number A. A is I e to the I pi over 2 k plus 2. So if you have a particular quantum field theory indexed by this integer k, you can write these down as Chern-Simons theories, as a sort of gauge field theories. You plug in the appropriate coupling constant k here. You evaluate your knot using the Kaufman rules with this particular value of A, and it gives you the probabilities in the output of these types of experiments. Now, what's more remarkable is that these things, these topological quantum field theories, are not just a figment of Ed Witten's imagination. They are known in the laboratory, and this gives me an opportunity to define what I mean by topologically ordered matter. So topologically ordered matter, the title of this talk, is any physical system that you actually have in your laboratory where at long wavelengths and low energy, it's described by a topological quantum field theory. So anything that's basically described by a topological quantum field theory, we call it topologically ordered matter. I'll give you a list of some examples. They come in various classes. Maybe the most studied right now is known as the SU2 level 2 class. That includes the so-called nu equals 5/2 fractional quantum Hall effect. I'll say some words about fractional quantum Hall effect later. There's various superconductors, strontium ruthenate being primary among them, so strontium ruthenate films. So I should say that fractional quantum Hall effect is an effect that occurs in 2-dimensional electron gases. So as I promised you, I'm a 2-dimensional guy, 2-dimensional system plus time as the 3rd dimension. So here, fractional quantum Hall effect lives in 2 dimensions. Strontium ruthenate is a 3-dimensional superconductor, but you can make thin films of it to make it 2-dimensional. Helium-3A. Remember that helium has 2 isotopes. You take the 3 isotope of it and you make it, cool it down to some very low micro-Kelvin temperature. It becomes a superfluid, and you make a film out of it. It lives in this class. There's a whole bunch of things known as Majorana systems, which usually involve superconductivity, spin-orbit coupling, spin-orbit, maybe magnetic fields, all stuck together. There's a lot of engineering going on of people trying to build these things in the laboratory and play with them. It's been going on quite a bit in the last couple years. There's another class that people have studied, SU2 level 3. There's really only one physical manifestation of that I'm aware of, nu equals 12/5 fractional quantum Hall effect. And then these are the ones that have actually been observed in the laboratory, to my knowledge. There's lots and lots and lots of proposals of how else we might build physical systems which are topological quantum field theories. They just haven't been done yet. Okay. So before going on, actually, any questions so far? No? Good? Okay, before going on, I want to do just a tiny bit of truth in advertising, because what usually happens after I give this talk is people go home and they try to calculate the Kaufman invariant of their favorite knot, because everyone has a favorite knot. And then what happens is they get stuck and they get upset with me, and then they yell at me, and I don't want people to yell at me. So I'm going to explain to you where the little glitch is in calculating Kaufman invariance, and that way you won't be upset when you try to calculate the Kaufman invariant of your favorite knot. Okay, so to explain this little issue, I'm going to take like a little piece of string like this that's looped just in a little loop like this, and I'm going to try to calculate its Kaufman invariant. And I mean for it to actually be connected up with some other bigger knot way over on the left. I'm just not going to draw the rest of the knot. I'm really just focusing on this little piece. So to evaluate the Kelvin invariant, I have to use the first crossing law over there. So let me do that. So it's A times vertical plus A inverse times horizontal. And then this goes off to the left, and this closes up. This goes off to the left, and this closes up. And then this loop is going to be worth D. These two can both be pulled straight. So we get A, D plus A inverse times a string that basically goes off to the left like that. And with a little bit of algebra, you can show that AD plus A inverse is actually minus A cubed. So this loop, the little looped piece of string here, is equal to minus A cubed times a straight string. Now at this point, you should be very upset with me. And the reason you should be upset with me is because I promised you that if two things could be deformed into each other without cutting, then they should have the same Kelvin invariant. And now I just showed you that this little loop and this little straight line can be that look like they can be deformed into each other, actually differ from each other by a factor of minus A cubed. So what's going on? Did I lie to you, or did I not lie to you? Okay, so of course I didn't lie to you, because I'm a nice guy. I wouldn't lie to you. The issue here is that this picture and this picture, although they look topologically equivalent, they're not. And to see that, you have to imagine thickening this line into a ribbon or like a tube, like a garden hose, something slightly thick. And if you imagine trying to pull this tube straight, like if you've ever done this with a garden hose, you know what happens. It ends up looking like this, right? Everyone knows how this happens. And this is not equivalent to this. This is straight without a twist, and this one has a twist. So this factor of minus A cubed is there to account for the self-twist. Now this is something that we actually should expect in quantum mechanics, because we know in quantum mechanics, if you take a particle just sitting there and you rotate it around its own axis, it can pick up a phase associated with its spin. And you'll notice that this factor of minus A cubed is just a modulus 1 phase. And this is what this factor is doing here. It's basically giving you the spin associated with this particle. And in fact, the connection between this picture and this picture is a really slick proof of the famous spin statistics theorem. You know, the spin statistics theorem that tells you that the phase you get for rotating a particle around its axis is the same phase you get for crossing over two identical particles. Well, that's what you have here. In this upper picture, you have two identical particles crossing over each other. In the lower picture, where you've pulled it straight, it's one particle rotating around its own axis, and these two have to have the same phase. Okay, so with this little glitch, you have to worry about the fact that these strings should be thought of as being thick. Then you can go home and you can calculate the Kelvin invariant of your favorite knot, and you won't run into any troubles. Any questions? Yes? Yeah, so you can close the ends like this, if you like. And this one is the same as a loop like this with a twist in it. Okay, can't draw it, but like this. This thing is a double twist. Okay, I can't like this, and then one more, like that. If you take this thing and you try to straighten it, it will look like this. This one will be a minus A cubed times D. It picks up a factor of minus A cubed, but for undoing that loop. Yeah. Okay? Good. All right, let me say just a couple more words about what makes Kelvin topological quantum field theories interesting in general and different from other physical field theories and quantum mechanical systems that we know about. So let me imagine we have a physical system, again, two-dimensional system, and we'll start it initially in its ground state, and then I'm going to put in it a couple of particles and antiparticles. So here's two particles and two holes. Now, in most physical systems that are gapped, have gapped excitations, and a unique ground state, once I say I start in the ground state and I put a particle here, a hole here, a particle here, a hole here, I have basically told you the wave function of the system. And this would be true for an insulator. This is true for a superconductor. This is sort of generally true for quantum mechanical systems. You tell me what all the local quantum numbers are, you've told me what the wave function of the system is. In topologically ordered matter, in topological quantum field theory, that is not true. That you can have two physical systems where I tell you I'm going to put the particles in the same places and the holes in the same places, like this, and those are supposed to look identical. They look identical. All the local measurements I can make on them are identical, and yet these are two linearly independent wave functions. How is that possible? So I'll call this one 1, and I'll call this one 2. How is it possible these aren't the same? Well, the way it's possible these two aren't the same is because in topological quantum field theories, you have to think about the space-time history of what you made. So there's two possible space-time histories. There's this. I could have pulled these apart from each other, or I could have done this, pull these two apart from each other. And these are topologically distinct. Those are different space-time histories, and so they can be linearly independent. To prove to you that these things are linearly independent from each other, I have to start taking inner products. I have to take overlaps. So to do that, OK, here I have my kets. I can also have bras. So the bras, same state, but I'm going to return things to the vacuum in exactly the opposite way. So this is the bra associated with 1, and I can make the bra associated with 2. Exactly like this. OK? And if I want inner products, what I do is I squeeze them together, bring the bra next to the ket. So for example, if I want inner product of 1 on 1, here's my physical system in the middle, like this. And it's the ket going down and the bra going up, like this. That's 2 loops. 2 loops, and the Kelvin invariant is d squared. If I do it with 2 on 2, like this, again, I start with the particles in the middle, and I have the bra on the bottom, the ket on the top. That's also 2 loops, and that's d squared. However, if I do 1, 2 overlap like this, in the middle, I have 1 on the top like this, 2 on the bottom like this. That looks like this. That is actually 1 loop, and that's worth d. Okay? So the fact that the inner product of 1 with 1 is the same as the inner product of 2 with 2, but the inner product of 1 with 2 is different, tells me that these are linearly independent states, unless d has modulus 1. If d has modulus 1, then they can all be linearly dependent again. That typically doesn't happen unless, actually, k equals 1, it does happen. So we throw that one out as being not very interesting. Okay. OK. Question? Yeah? Yeah?
So when defining the state, there is a phase amplitude.
Yeah, that's not going to, you're saying that this can be, so I get rid of the phase here, and I get rid of the phase here because I'm using both the bra and the ket. But this one can have an arbitrary phase associated with it. That's yeah, no, well, you have to make a convention for it. Yeah, in this case, the convention is made to match the Kelvin invariant. In fact, you can also notice that here, these kets and bras are not normalized in the usual way. So you have to worry about that as well. But still, it will show you these are linearly independent. Yeah. You can do other things as well. For example, you can imagine making an inner product which is 1 and then some complicated operator, which I'll call braid, which braids the particles around each other, 1. So I'll do that in this picture here. So I'll put between 1 ket and 1 bra, I can put some complicated braid, like this, that, and like this, and over, and like this, and maybe under, and like this, and this one goes like this, and I don't know, something like that. And I can calculate the inner product of 1 operator 1, again, by evaluating the Kelvin invariant as I like. You can think of this, if you want, I have this 2-dimensional Hilbert space associated with the ket 1 and 2, and the braid is doing some rotation within that 2-dimensional space, and then I take the projection onto the 1 state that way. That's another way of thinking of this. Now, This brings me to the second part of my title. Why should anyone care about this? Well, I'll give you a hint. If instead of writing this as 1 and 2, I had instead called them 0 and 1, people would have immediately thought, oh, it's a qubit. You're going to build a quantum computer out of this. And indeed, that's exactly why it is that people are interested in this, because this is actually a really clever way to think about building a quantum computer. So let me say a couple of, actually, someone once said that any idiot with a two-state system thinks they have a quantum computer. And it's my objective to prove to you that I'm not just any idiot, that this is actually a reasonable thing to think about doing, and actually it's a fairly good idea. OK, so let me be a little bit more specific about how it is one would imagine building a quantum computer out of this. And I should also give appropriate credit. The people who really thought up the idea of building a quantum computer this way are two people who I think are it's justifiable to call them both geniuses. One of them is Mike Friedman, who's also a Fields medalist for his work on the Poincare conjecture. And the other person is Alexei Kitaev, who is one of the people who is sort of a real leader in actually several fields of physics these days, sort of a rather brilliant human being who came up with a lot of these ideas quite a while ago now. So the general idea of what we're going to do is the following. Here's a two-dimensional system, and again, time is going vertical. And what we found is when we had 2 particles and 2 holes, we had a single two-state system. That was 1 qubit. So if I want to make a qubit, I just pull 2 particles and 2 holes out of the vacuum like this. If I want 2 qubits, I'll make more. And then 3 qubits, 4 qubits, and so forth. So now I have 5 qubits in my system. If I want to do some quantum mechanical computation, a quantum mechanical computation is really some unitary operation on this space. The way you do that is you just rotate the particles around each other, drag them around each other to form some complicated knot. OK, form some complicated knot. Da-da-da-da-da. OK, all right. OK, here's a complicated knot. And then at the end of the day, you bring them back together. And the readout is that some of them are going to annihilate back to the vacuum, re-emitting their energy, and some of them will not. And that will be the information of the readout. Now, a couple of things I need to convince you. The first thing I need to convince you is that you can actually do quantum computations this way. The second thing I need to convince you is that it's a good idea to do it this way. So the first one is actually fairly easy. So you'll remember back at the beginning of the talk, I said that calculating the Kelvin invariant for a complicated knot is something that's exponentially difficult. That with a complicated knot with 100 crossings, the biggest computer in the world could run through the edge of the universe and never be able to calculate the Kelvin invariant. But suppose you had a topological quantum field theory or some topologically ordered matter in your laboratory. There's a very, very good way to calculate the Kelvin invariant, or at least to estimate it very accurately. And that would be to take your knot, form the knot physically out of all your particles, drag them around each other to form the knot, try to annihilate them. The probability that they all annihilate is exactly given by the Kelvin invariant of that knot actually squared. And by just doing it many times, you can get an increasingly good estimate of the Kelvin invariant, which is something that a classical computer could never do. So that tells you that the Kelvin invariant quantum computer that we just built here with these particles living in our laboratory, maybe built from one of these physical systems that I wrote down over here, has some computational ability beyond what the classical computer can do. Now, that may not be so interesting because you may not stay up at night saying, I wish I had a way to calculate Kelvin invariance. But it turns out, and this I won't prove to you, but the ability to calculate the Kelvin invariant for a very complicated knot is equivalent to the ability to do quantum computation of any other quantum computation algorithm like factoring large numbers or Grover search or anything like that. Okay? So that at least should give you a hint that this topological quantum field theory computer can be quite powerful. Now the other question is, why would you like to build a quantum computer this way? There's lots of people in the world who are interested in yes? It is actually, I believe it is, I'm not sure I even know what these words mean, but you probably will know. It's sharp P hard, which is harder than NP complete, actually, is my understanding. So it's believed to be worse than yeah, so it's exponentially, the short way to say it is it's exponentially difficult. Okay. Okay, so the other thing I have to explain to you is why is it you would want to build a quantum computer this way. There's a lot of people in the world who are interested in building a quantum computer, and there's lots of techniques, some of which are looking fairly promising. So what's good about this particular technique? Well, what's nice about this, to understand what's nice about this particular technique, you have to understand what's hard about building a quantum computer in the first place. When you build a quantum computer, so the conventional picture of a quantum computer is you have a whole bunch of two-state systems, maybe spins. And you put the spins in some complicated states, some complicated superposition, and you do operations on those spins. Then you make a measurement at the end. The problem is if in the middle of the computation some noise comes in, say a photon, something out of your control, flips over one of the spins, it just made an error in your computation. And due to the quantum no-cloning theorem, it's very hard to protect your system from these errors. Now, there are quantum error correcting codes which can help you keep yourself isolated from these kind of errors, but they're fairly complicated and difficult. Now, let's think about what happens if you're in the middle of one of your topological quantum computations here, and some noise comes into the system and hits one of the particles here. What happens when the particle gets hit by the noise, say a phonon or a photon or something like that? Well, what happens is the particle gets shaken around. Okay? So the particle, instead of taking a perfectly smooth path, it takes a wiggly path. But as long as the topology of this knot has not changed, as long as you did not change the knot, you didn't make any mistakes at all. Because the only thing the topological quantum field theory is sensitive to is the overall topology of the knot you made. So in some way, this topological quantum field theory is inherently deaf to small amounts of noise, and other quantum computers don't have that advantage. And that's why people are interested in this approach. I should also say that in the modern era, some of the approaches to quantum computation, especially some of being done by Google and IBM, are doing extremely well. That they're really making a lot of progress. And the honest truth is it's very hard to come along and say, I have a better idea than you do, because these guys are really making quite a lot of progress right now. However, even then, at the end of the day, they all accept that they're going to need quantum error correcting codes. And the best error correcting codes that are known are basically constructing a topological quantum field theory out of individual qubits and then going from there. So somehow they're going to simulate topological quantum field theories and use that to error protect their qubits at the end of the day. So whether or not we're going to use one of these physical systems or we're going to use one of their systems, at the end of the day, what we're doing is probably related to this in one way or another. Do I have a few minutes left, or should I stop there? A few minutes more? I just want to say a couple of words about some of the topologically ordered matters on this list. So I have this list over here of interesting topologically ordered matter. Maybe fractional quantum Hall effect is the most interesting one. It's certainly the one that's been most studied at this point. So let me say a couple words about what is fractional quantum Hall effect. Fractional quantum Hall effect. So basically, the theorist picture of fractional quantum Hall. Are there any experimentalists here? 1, 2, 3. OK, 4. So you guys are probably going to want to strangle me. So I'm going to explain fractional quantum Hall effect in 2 lines. You take 2-dimensional electrons, you add a magnetic field, you cool it down to low temperature, and out comes fractional quantum Hall effect. It's really that simple. OK, that's why experimentalists hate me. So there are different fractional quantum Hall effects which are indexed by this thing nu, which is basically the dimensionless ratio of the number of electrons divided by the magnetic flux in the system. You need to get it close to some nice integer ratio, like 5/2 or 12/5 or something like that, and each one of these has some different property. And the question is, how do we know that this fractional quantum Hall system is actually some sort of topological quantum field theory? Well, these physical systems, you do the experiments at temperatures well below a Kelvin. There's not a lot of experiments that are easy to do. In fact, there's only one experiment that's easy to do. It goes like this. You take your two-dimensional sample, has some arbitrary shape, and what you can do easily in these experiments is you can attach electrical contacts to it. So let's put current between these contacts and measure the voltage between these contacts, like this. Okay, it doesn't matter what the shape of the sample is. It's some arbitrary thing. The contacts can be some ugly thing, soldered on the edges in some very ugly way. When you do the experiment in this way, you get a very simple result that the voltage is 0. There's a longitudinal voltage. Comes out 0. That's what you would get if you had a superconductor. It doesn't support any voltage. You have perfect dissipationless transport in this system, so it looks like some sort of superfluid. So that's kind of interesting, but it's not the really interesting part. There's one other experiment you can do, and it's very similar. I'm going to change the experiment a little bit. I am going to topologically cross the current and voltage leads, like this. Okay? So now I'm going to run the current from here to here and measure the voltage from here to here. This is a Hall voltage measurement, the Hall. And what you measure is the current times a factor, h over e squared. H is Planck's constant, e squared, that's the charge of the electron. 1 over nu. Nu is this small integer ratio, 5/2 or 12/5. It's some set of integers. Let's call it p over q. So this is p over q, some integers. And it's quantized extremely precisely. This number, fundamental constants times integers, is quantized so precisely, it's like a part in 10 to the 9 has been measured. That's like measuring the distance from here to Los Angeles to within a millimeter. So it's an incredibly precise experiment, and it's done on a sample of any shape, any size, with ugly leads that have been soldered on, really complicated, in some messy way, with disorder in the sample. It gives you a hint that something is topologically protecting that output. You compare that to making a resistance measurement on a piece of copper. When you run current through a piece of copper, it matters completely where you put the current, where you put the voltage contacts. You move the voltage contacts a little bit, the voltage changes entirely. So with one more comment, once we have this thing and it looks like there's some sort of topological protection, that gives us a hint that what we have is a topological quantum field theory of some point. And I guess for people who are high energy field theorists, or high energy people who study high energy physics, I just want to comment here that there's in high energy physics there's this general paradigm of symmetry breaking, that out there's a grand unified theory which is very, very symmetric, and you cool down to low temperatures, the temperature around us, and you get symmetry broken from the high energy theory. And here it's exactly backwards. At high temperatures, there's not much symmetry at all, but you cool down to low temperature and you get this topological symmetry, which is highly, highly symmetric, and it's emerging at low energy scales rather than breaking at low energy scales, so it's slightly backwards. The last thing I want to say is in this topological quantum field theory, in this fraction quantum Hall effect, what is it that we're dragging around each other? Well, this is a dissipationless fluid. And in dissipationless fluids, you have persistent vortices. You have currents that will last forever, just as Kelvin was telling us. And these persistent vortices will give the quasi-particle excitations, the particles in the holes, that we want to pick up and grab and drag around each other. So this is actually not too, they will last forever because it's completely dissipationless. They carry charge, but that's sort of irrelevant. We drag them around each other, and these are the things that we're going to form into these knots, into these Kaufman invariants, in order to do these topological quantum computations. So it's really actually quite similar to what Kelvin was thinking about 150 years ago. The only thing that's different is that he was thinking in 3 dimensions, and his vortices formed lines in 3 dimensions. And here, we're thinking in 2 dimensions. The vortices are points, but then we have time as the 3rd dimension, and we're forming knots in 3-dimensional space-time. Other than that, Kelvin, he more or less had it right, or Peter Tate had it right. Of course, it has nothing to do with the periodic table of the elements, but it's still quite interesting for the future of quantum computation. So I'll thank you for your attention, and I'll take any more questions people have. Yeah, okay. So you're saying that with that knot, there's one cup at the bottom, and there appear to be two caps at the top. Is that what you're worried about?
Yeah.
Yeah. So you're right. Somehow you have to deal with that. One thing you could do is you can imagine bending this over so that you have two cups if you wanted to. You're allowed to cut the system anywhere you like. You can cut the system, you can do this and cut it here if you want. And you can take the inner product between this and that if you want. So the topological quantum field theories will allow all of these possibilities, and they all work out consistently.
So there is always a one-to-one correspondence between knots and the...
Well, not one-to-one, but you're allowed to you can make a bra and a ket by cutting at any point. It's not necessarily the case that you can't make the same ket with a different knot. But often it's hard to make them in simple ways with the different knot, with another simple knot. Okay, other questions? There was, well, okay. Go ahead, yeah. So one of the knot pictures. So okay, so this, we have to turn it sideways. So, okay, and then we have these particles that are, some of them are vortices, some of them are anti-vortices. That's like particles and holes. So we have particles and holes. And then in order to make these vortex-anti-vortex pairs, at some point in the past, the vortex-anti-vortex pairs had to pull apart from each other as quasi-particle, from 0 to particle vortex-anti-vortex pair. That would be the bottom, like this, and then you can move them around and bring them back together. Does that make sense? So the electrons, the fact that I'm running current, throw that away. That's not interesting to us. That just gives you the Hall conductance. What we're interested in here is just the property of the quasi-particles. There was another question here. Yeah. Okay. Yeah. So. Yeah. So let me be honest about it. So starting around 15 years ago, people got very excited about doing this with the fractional quantum Hall effect. And fractional quantum Hall effect has turned out to be exceedingly difficult to do any manipulation with. And then people are still doing experiments trying to show how you can manipulate quasi-particles in the fractional quantum Hall effect. But the data is fairly murky and very messy. So the new approach now is these sort of engineered Majorana systems. And there's lots and lots of designs for what it is people are going to do with that. Now, those have turned out to be a little finicky as well. I would say there's a lot of effort going into manipulating them right now. It's unclear if it's going to be successful, but there's no fundamental reason why it shouldn't be. It's a question of how much engineering they're willing to do on it, I think. They'll probably be able to do this at some level. And I can sort of explain some of the detailed ideas. You have, there'll be, some of these things are electrically charged, or some of the physical systems have electrical charge, and you can have they sort of have this picture that looks like a bunch of piano keys, and you can sort of gate off regions of your system to push things to the left and then push things to the right, and sort of move them down alleys and move things around and so forth. So there's various schemes of how it is people want to manipulate these things. It's, they're very clever about designing them. It's just making them actually happen in reality has been difficult.
That sounds sort of mechanical, and is there a worry that it will never be fast enough?
Well, no, I think that's not really a worry. That there's a time scale. So what causes problems? I mean, the thing that can cause problems is if you have decoherence that you can't control. Now, the idea is that these things are very immune from most noise. They're not completely immune. There are still things that cause problems. The thing that can cause problems is if a stray quasi-particle shows up in your system and forms a knot around a bunch of particles and ties itself off to change the knot from what you intended. And there is some time scale associated with that, but they think they can make it very long so that it's not going to be an issue. At least that's the current thought. And there's reasons why you could argue against it. I mean, the people like Deveray, who was here last week, they've done a lot of experiments on superconducting qubits, and they found that one of the issues which they're working on very hard. I mean, I think all of the solid-state quantum computing people are really worried about is that you sort of think you take your physical system and you cool it down to lower and lower temperature, and then stray quasi-particles and stray excitations, they disappear exponentially. That's what thermodynamics tells you. But it turns out that's not true. That thermodynamics doesn't really work because things aren't completely in thermodynamic equilibrium as much as you think they are. There's always some stray things that are somehow managed to stay out of equilibrium. And when you're really worried about single events, you have to worry about the small part of your system that somehow hasn't thermally equilibrated with the rest of the system for some reason. And there's been a lot of study of this and worrying why it is we still have some excited quasi-particle even at 10 millikelvin. So there are issues like this that could cause trouble, but they're basically trying to engineer around them. So, yeah, and then you next.
So it seems like the Kaufman invariant doesn't do what it's supposed to do, really. That you said that there's two knots that are different.
That's right. That's right.
So, or is it just it works the other way, in that if they give two different Kaufman invariants, then you're sure that they're different?
That's correct. That's exactly correct. Yeah. It's able to distinguish things from each other, but it can't prove to you that they're the same. Yeah, but for doing a quantum computation, that's all you need. Yeah, that's equivalent to quantum computation in this case. Good. Yeah. Why these particular fractions? So this is there is a reason why we've chosen these, but it's not easy to explain. So each fraction that's been observed in nature, there's been a lot of numerical work trying to figure out what the character of what physical phase of matter are we looking at. And all of the numerical simulations tell us that 5/2 is related to this SU2 level 2. I think there's very little doubt that that's true, and with pretty good evidence, we think that 12/5 is related to this SU2 level 3. And all the there's tons of other quantum Hall fractions that are out there, and almost all of them are closer to k equals 1. And k equals 1 was this funny case where d comes out to be 1, and therefore the 1 state and the 2 state are actually linearly dependent on each other. They're equivalent. So you're not able to do quantum computation with, say, nu equals 1/3 or 2/5 or 3/7, or at least as far as we know you can't. Although actually there have been some very clever tricks that people have cooked up to try to be able to do that as well, but I don't think anyone thinks they're realistic. So, yeah. 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 Well, I is the current. You're allowed to put in whatever you like. You put in current, yes. You put in current and you measure voltage. Yeah. This is a circuit diagram for a current. It says you put in the current and you measure the voltage. So this is a meter, and this is a source. Yeah, current source. Yeah.
So this is kind of related to the previous question. It still feels that you have at least two levels of topology, right? That, for instance, if you take various fractions of all phases, you cannot go from one to the other without closing gaps.
That's correct.
Because these are topologically protected. But then some of those phases are even more topologically protected in more the time space.
Right. Just
View it because they have some statistics, whatever. And where is the link between?
yeah. So actually, all of the fractional quantum Hall states are topological quantum field theories, but it's only the very few of them which have this property that there are multiple wave functions with a fixed number of quasi-particles. That's the non-abelian property, which is fairly unusual. It's actually kind of a miracle that it exists at all, but it appears to exist. I'm not sure I can say more. They all are topological in this sense, that, but there's very few of them that have this particular property.
So yeah, I guess it's also related to the fact that in most of the cases, D would be equal to 1.
Exactly. Yeah. Exactly.
Some kind of higher order of
Yes. Some are better than others, and it's just a gift from nature that we happen to be able to access a few of the interesting ones. I mean, I guess nature could have been more kind, and maybe all of them could have been interesting, but nature has been at least fairly generous to us. Yeah. Yeah. Anything else?
It seems that part of your problem is classically complex, but why you need quantum complex? When, for instance, if you have a law that is complex,
Yeah.
you can make it unlike that with some.
Yeah. So let me give you a challenge. So if I give you a knot with 100 crossings and hand it to you on the table, and another knot with 100 crossings and hand it to you on the table, and ask, can you deform the first into the second without cutting? You'll be sitting there for a long time trying to figure it out. Let me put it that way. So, yeah, actually, to be more specific about this, Peter Tate's knot table went up to something like 9 crossings, okay? And he enumerated all the possible knots you can have up to, I think, 9 crossings, something around that. And so there's a lot of knots that he enumerated. And it was 90 years before someone discovered there was one error on that table. With yarn. I mean, they actually figured it out with yarn. Yeah.
Set up a probabilistic measure on the possible knots. So
Yeah. Yeah.
for example, you start to draw random knots, and then you take 2 and which have the same number of knots,
Yeah.
and then you have to use the probability that the 2 are the same.
Yeah. Okay. So there's various random knot protocols that people have studied, and they can ask what's the overlap between the kets that you can get. What's the typical what the typical overlaps? These questions people have studied. I don't know the answers to them offhand, except for in some very rare cases where I might know some answers. But these become interesting stat mech and probabilistic problems that are fun to play with, and so I encourage you to do so. So.
So for the quantum theory, was to find the Simon series for any gauge group, like this where
Yes, you can. Yes.
isn't any analog on the website for those where
Yeah. So it's true. We could have chosen any gauge group if we wanted. It turns out most of the physical things that we've seen in matter in reality are SU2 level something for some reason. That just seems to be the simplest. It seems to occur most often. There's one physical system that may have been seen, another fractional quantum Hall state with 2 spin species, which is believed to be SU3 level 2, but it's not 100% certain. And I think that's pretty much it. So it just so you can certainly discuss these. I mean, I guess there's one which is a abelian BF theory, which may have been seen in matter as well. It's abelian, but it's a little bit more complicated. But you can sort of think of BF theory as kind of being like Tucci-Simon's theory, so it's not that new. But yeah, you're right. I mean, you could have thought of E8 level 16 or some crazy thing like that. It's hard to find them in nature. I mean, people have ways of cooking them up in various models, but actually realizing them is hard. So, anything else? All right. Thank you very much.